have interaction among the students with the faculty, and it is more about understanding each other, work with the academic part of it is also to speak, telling about your work to your fellow students. I know internally, or you might be discussing it, but it's also good that you are doing along with the faculty members. And here I have requested Professor Apparao and Professor Guru, Dr. Guru. Both of them will be as a coordinator. Like, if you have any support, like you have one or two student representatives, so you have to take this PhD seminar on their own. So first, as a kickoff, Professor Srikanth agreed. Let's start from the faculty side. But at the end, it is important that you guys come up, make the plan for the whole week, whole year. Let's say there are 52 weeks, so you can think of like a calendar, at least plan a calendar semester-wise, and can also make it like for 1 month or something. So include that. So I want that type of activity to be initiated. So that's the idea. I don't know whether these representatives are Ranjit and where is Ranjit? Yeah, Ranjit is here. So did you make that list? So anybody agreed that list? So I mean, to be more informal, but at the same time, it is also important to stick to the certain principles in the sense to improve our academic part, or also the presentation part, and also, how to ask questions and also expose yourself a little bit more. So that's the point. And it happens in all around in the school. We also to do that in our school. That's the point, actually. And one, two things. I don't know if I know other things forgetting about this. So this is just in that fashion. Please, maximize your number. And next time onward, I don't want to speak. I want one of you to speak and coordinate this. And beyond that, so that's why in the timetable you might have seen that PhD seminar also set it up like that. So this is the time we have it free. Friday afternoon, 4 p.m. Luckily, what happened? Tomorrow is supposed to be 26th of January. So we thought it let's prepone it and do it today. But next week onward, most of the time it could be the Friday 4 p.m. That is the fixed date. So I hope, I think for the next week, is anybody ready already? No. Ranjit, who is ready for the next week? Okay. Anybody can raise the hand? Volunteer. Volunteer. Based on this, how it goes there. Green and red. How many of them are the 5th year students? 4th year, 5th year. They are not. They are all new. Please come forward. Please come forward. Please come forward. Please come forward. Difficult to pick the volunteer, but I'm happy that you guys have done well during the conference. That volunteer, they really shown the talent of in all respects, and it was a wonderful cooperation from all of you. This is also a kind of activity to spread for your own benefit. So I will. Otherwise, what will happen? We will make a lottery, or Guru and Dr. Apparao will make the lottery, and then see who's not paying comes in the room. These can announce some incentives. That is also a good point, actually. That's an interesting point. That's yeah. That's not the incentives. Yeah. Maybe for the first one, I will how to say offer some price. Maybe the toy one. It will not be green. Yeah, that is a good point. I think I will take that into account when you are doing the presentation. That assessment will be there. We will give appreciation. I think it's a wonderful thing to take that. So that will also good thing. Okay, I think I will not take much time. I'll invite Professor Srikanth. Everyone knows him. And, yeah, if you want to introduce about him, I think not introduce. Yeah, because he's coordinating. Yes. Yeah. That's good. Very good afternoon to all of you. Very good practice. He was the director and he was also the vice chancellor. He used to ask us, we were and scientists, every Wednesday he used to ask us what you are doing. Irrespective of your one or two slides. Only slides were not there. Transparencies we used to make a transparencies we used to present it. So this will become a strong foundation. How what you are doing, how to present it for any other forums anywhere. So it will be a very good practice, and I think you all come forward, and myself and Dr. Guru Vidyadi will be looking after this, as our dean made a mention just now. So definitely whoever does well, some recognition in the form of some some certificate or at least something will be given. So thank you, and I would request Professor Srikanth to proceed with the presentation. Thank you.
Yeah, thank you. Am I audible? Okay. Yeah. No problem. So the main premise, as you heard, is for this presentation is such a gathering. So let us continue this every week. Let's not and you should volunteer because you are in the final. Friday, every Friday. If you make a practice, actually, as they said, it will be very useful. So I volunteered because I was ready with a couple of presentations, and this is one of the presentations I gave recently in when we visited Singapore. So I thought I made minor modifications to it to suit you. So the basic premise, apart from this gathering, is there are a lot of lacunae in understanding green energy technologies. And these green energy technologies come with a great hype rather than the reality. So I'll take well-known examples to highlight lacunae, and I'm sure most of you will connect to these examples. I will not only pose the problems, but I also have certain recommendations which we as material scientists or materials engineers doing research with in materials engineering can incorporate in our research and connect to these green technologies, including green energy tech. Unfortunately, we have most of us have a problem in comprehending the basic definition of technology. You might have seen many people, telling that my process is a green process, my synthesis process is a green synthesis process, my technology is green technology, but without doing thorough explanation about why your process or synthesis process or whatever is being. In other words, there are several descriptors. Only when all those descriptors are satisfied, you can call the process or anything green. So we should not use this terminology loosely. That's very, very important. And you see As I show you the lacunae, you will hopefully will connect to these problems. Uh, or no? Yeah. Okay. So I'll have a couple of slides which are very basic in nature about the energy consumption, energy requirements for the future, um, and also certain aspects related to sustainability. You might have heard this buzzword sustainability these days. And then I'll present, I'll take three examples in energy conversion, storage, and transportation, uh, and identify or highlight the lacunae, and then the recommendations. Okay. So uh, when we consider the energy consumption and requirements for the future, on average, worldwide, as of now, we are consuming about 580 million terajoules per year worldwide. Okay. When I say energy, it doesn't mean electricity. It includes all forms of energy together. With the increasing population, it is estimated that by 2050, the population would be around 10 billion, and accordingly, the requirement for by 2050 will be about 900 million terajoules per year. So if you want to comprehend what 1 terajoule is, so if you take a Boeing 737, it's very specific when I say, because when we do calculations in our research, you should be very specific to what you're doing. So I'm taking this vehicle 737 and do my calculations of how much energy is spent when I board this particular machine or aircraft and travel from India to fly from India to USA. That's about, let's say, 10,000 kilometers. Okay. So for one travel of, let's say, taking this machine, if you calculate the energy consumption, it is 1 terajoule. Okay, so now you can comprehend what this number is. 580 multiplied by 10 power 6 multiplied by 10 power 12 joules per year. Okay, that's not a small number. Now, with these requirements, present and future, we have to meet these requirements, keeping environment into uh, uh, consideration. We don't want, while consuming this much energy, we should not cause problems to the environment. Now, if you see, if I am expending 580 million tera joules of energy per year, uh, that equivalent greenhouse gases production is about 50 billion metric tons. And out of this, about 35 billion metric tons is alone of carbon dioxide emissions. Okay. If you include other greenhouse gases, it is about 50 billion, 10 power 9 metric tons of greenhouse gas emissions. So you have to also deal with this while expending so much of energy. And what is the requirement? If you see the requirement when we talk about 900 billion in requirement for 2050, we are talking about bulk conversion, bulk energy storage, bulk energy transportation. And the requirements are in industries, for commercial transportation, for residential purposes, all that put together, we need bulk energy conversion systems, bulk energy storage systems, and bulk energy transport systems.
Okay, this is very important. Now, of late, this sustainable development goals have come into the picture. In this context, United Nations and member states of United Nations have decided in 2015 that in order to protect our environment while meeting the energy requirements and other environmental requirements, it is important for all of us to achieve these sustainable goals by 2030. 2030. They have decided in 2015. We are in 2024, and we have to. And if we, there are 17 such goals classified. You can read those names. Under each, there are different tasks. There are about 169 tasks. So, in order to achieve those, a particular plan is given under each head. Unfortunately, the average is not even 50 till now. That means we have not even reached the 50% of the SDG goals, and these are interlinked. What I mean by interlinked, if we talk about quality education, if we don't achieve quality education or the descriptors under quality education, several other developmental goals are affected. Likewise, if we don't achieve clean water and sanitization as given under the SDG 6, we will not be able to achieve good health and well-being. Likewise, several other SDGs are interlinked. In our case, in the context of this presentation, SDG 7, which is affordable and clean energy, is very important. So you see that the United Nations has used clean energy, not green energy. Okay, so I'll also clarify about the definition, the difference in clean energy and green energy. Now, clean energy, this SDG 7 is linked to 9, 13, 15, and also 11. And if you do any if you develop any wrongly engineered green energy technologies or clean energy technologies, it is going to adversely affect achieving the other goals, because you will be hindering achieving the other SDG goals. Now, let us see what the overall score of the Sustainable Development Report till now. If you consider the overall score, I've put different countries here. If you see, the Finland has achieved about 83%, and they're close to 100%. They're approaching 100%. If you see Germany, it is at around 83, and India is around 63. Okay, we are also doing well. We don't know because we never saw this report until I displayed it here. I know. But we are far away in comparison to the other countries like Finland. Of course, they're small countries, but they are doing very well. Now, when it comes to the energy, if you see here, India is also not doing very well in comparison to other countries in providing electricity, for example, to all the population. It is still not 100%. When there are many sectors or many places where electricity is not reaching the people. So that's 100% is not there yet. But if you see, the incorporation of renewable or clean energies in providing electricity to the population of India, India is actually doing better than China and United States, that means United States is also a big country, but when you consider their energy sources and our energy sources, we are incorporating renewable energy sources more into the energy conversion and provision of energy to the public than United States and countries like Japan. They're still using that means they're still using more non-renewable sources, but still, please keep in mind they're doing very well in the overall SDG, because in other aspects they're taking care of. Like, for example, quality education, sanitation, and all, they're doing very well. Now, let's come to the definitions. As I said, unfortunately, we don't comprehend the definitions very clearly. So it is very important to understand what these clean energies are, what is renewable energy, and what is green energy. And you'll see that there are subtle differences among these. Clean energy, it is the energy when expended produces ideally no greenhouse gases. Okay. For example, conversion of solar energy to electrical energy, there is no greenhouse gases. Okay. It can be called as clean energy. What is renewable energy? It is the energy converted from a renewable source. The source is a renewable source, like solar energy is a renewable energy because the source is sunlight. Then what is green energy? It is the energy converted from one form to the other, or energy expended without ideally harming the environment. So there is a difference. So if you strictly go with these definitions, clean and renewable energies need not be green energies. Okay. If you did not understand, I have an example here. So this is our School of Life Sciences. They have on the rooftop a solar system, solar panel system. This is a 1100 kilowatt peak solar system with 100 kilowatt inverter. This converts sunlight into electricity. This whole system, when it functions at the peak, it converts solar light into 1.6 million units of electricity per year. 1.6 million units. 1 unit is 1 kilowatt hour. Okay. That means the energy expended if you operate a microwave unit in your house at 1,000 watts per 1 hour, the energy consumed is 1 kilowatt hour. Okay. So this system, when it works in the optimal conditions, it converts sunlight into 1.6 million units. Okay. Now, if when it is working in the operational conditions, and when we talk about the environment, if you have such a system under operation, you save about 1,300 tons of carbon dioxide. That means you're producing less, 1,300 tons of carbon dioxide less if this were not in use. Okay. Now this is per year. Now, well, let us apply the definitions on clean energy. Yes, solar energy. That means sunlight is converted into electricity, no greenhouse gas emissions. So it's clean energy. Is it renewable? Yes, because I'm using sunlight. But is it green? Why is it not green? It is not green because if we consider the full life cycle of the system, what I mean by full life cycle, I need essential materials, in this case silicon. It involves mining, processing, manufacturing of the panels, installation, assembly, usage, maintenance. And once all these components come, at some point of time, they come to the lifetime, you have to discard them. They get wasted. So if you consider the whole life cycle, these things which I've mentioned actually cause emissions, greenhouse gas emissions. Therefore, this is not a completely green energy technology. It is clean, renewable, but not green, if you strictly go by the definitions. Now, is there any example for green energy technology? Yes, probably the only available example is the natural photosynthesis. Sunlight is converted into chemical energy, into mass, chemical energy, clean, no greenhouse emissions. Renewable, yes, sunlight, renewable. Green, yes, green. It doesn't cause any environmental effects, but in addition, it helps the environment. Okay. Now, then in practice, we don't operate under those strict conditions. We are lenient. So we use this minimal environmental impact. So any technology that enables harnessing energy with minimal environmental effect, we call practically as green energy technology. If you strictly apply those definitions, none cannot can be considered as green energy technologies. Okay, but this minimal has to be really minimal when we do our research or development or technology development or bring any technology into the operation. Now, let us see what are the key green energy technologies that are available. These can be classified into different categories. One is conversion technologies, where you convert energy from one form to the other, like solar light, sunlight into electricity, or wind to electricity, biomass into electricity or other form of heat energy, likewise. Storage technologies, secondary battery technologies like lithium-ion battery technology, supercapacitors, they are all storage technologies. Okay, these what the storage technologies do. Their job is to support the green energy conversion technologies. They support where do you store the energy, because you know these some of these technologies when the sunlight is not there, for example, you know the system is developed to convert so many units, but you don't use all those units in one go, so you have to store a part of those in certain systems. Those systems are energy storage systems. They're also named as green systems, like lithium battery is named as green energy storage system, but you will see there are several lacunae and why we cannot strictly call it as a green energy technology. Then, of course, transmission technologies, which involve smart grids, because you have to transmit energy from one place to the other. You transport. Inverter, for example, is one system where what does an inverter do? This solar energy, sunlight is converted into electricity, but that's DC. You cannot use. So inverter converts the DC current into AC current. That system is also very important, and efficient inverters are very important. Developing efficient inverters without loss of while doing that, losses should be minimized. Of course, smart grids. These are basically for energy distribution, fluctuating. If there are any fluctuations in the, they accommodate such systems. They are smart. Okay. Why you should manage? Because losses can be controlled. Okay, that's in one way you save a lot of carbon emissions if you control the losses. There are allied technologies, for example, design approaches. You can enhance the efficiency of any system, conversion system, storage system, or transportation system if you bring in design principles rather than arbitrarily doing something. That is why you have standards in manufacturing your batteries and supercapacitors or any conversion. You cannot arbitrarily make whatever way you want. Okay, if you are making a solar cell, you have to follow a standard. You are making a lithium-ion battery. There are standards, codes, and standards. You have to follow that because they have been optimized. They have been tested time and again for efficiency and to minimize the losses. Okay, energy efficient machines, during manufacturing or machining or fabricating something, machines are important. So you need to also develop. These are allied technologies. They may not be directly called as green technologies, but these help in developing the green technologies. Of course, you have processes, manufacturing processes. That's very important. We'll see how the manufacturing processes play an important role in developing these primary green energy technologies. Okay. That is very important. Efficient monitoring and managing systems. Their electrical and electronics engineering is very important to generate data and see if there are any fluctuations, and then to bring everything, all the systems in a proper condition. Looping and all efficient looping system should be there. So there are several allied technologies which people don't work on. Very few people in the world, not just India, work on such allied systems. Okay, so even buildings, yeah, ventilation and the light coming, the natural light coming into the building, they're designed in such a way that you don't need air. They don't have air conditions. They don't have many fans. The building itself is designed in such a way that the airflow and the light and the ventilation is taken care by virtue of building itself. So you minimize the use of these and automatic lighting systems that when natural light is there, these won't switch on. Even if you want to switch on, they don't switch on. Okay, something like that. So you can also save a lot of emissions. You can do that by through efficient designing efficient buildings. Now, let me take this solar cell technology. I've listed several lacunae in this. Okay. Now, if you see solar panels like these, can constitute as high as double tonnage of all the global plastic waste. I'm not saying that. This is a report by this international organization. That itself, so you have plastic waste, that is another problem. But these solar panels, once they get wasted, they will be more than that of the plastic in terms of carbon footprint. Did you get the point? Plastic waste is there. We are already dealing with the problem. But if you consider the wasted solar panels, they can be much more dangerous than the plastic. Fossil fuel energy is expanded in manufacturing them. If you want to manufacture a solar panel, where is the energy from? It's burning the fossil fuels. How much raw materials have to be mined, transported, processed, subsystems assembly, etc., implying greenhouse gas emissions. Now, if you consider silicon solar cell technology, about 45 gram carbon dioxide equivalent per kilowatt hour energy conversion. So if I am converting and storing 1 kilowatt of power in a storage system, let's say, I am generating about 45 grams of carbon dioxide equivalent. Okay, that is a less number. But if you want to comprehend this number, if I am burning fossil fuels, let's say, that will be 100,000 grams. If I am burning fossil fuels to store 1 kilowatt of energy, that will be equivalent to 1000 grams of carbon dioxide emissions equivalent. So if I'm considering wind energy, that number is less, only 16 grams. It's much more greener than the silicon solar cell technology. But still, there are carbon dioxide emissions, greenhouse gas emissions are there. Now, when we make these solar cells, toxic chemicals are used. One of the important byproduct is silicon tetrachloride. It's so dangerous, and there is unfortunately no procedure to. It's not even here, not only in India, even outside, how to discard this silicon tetrachloride into the environment. Okay, nobody follows. There is no protocol. Similarly, in order to etch silicon, acids like, yeah, I'm also coming to that. Yeah, what he said is correct. Now people have moved to the 5th generation solar cells. There also there is a problem, but in any case, if I'm talking, this is only to identify towards the 5th generation solar cells. Elements like lead, cadmium, arsenic, etc. are used in them. These are again detrimental for the environment. They enter the system, processing system, manufacturing system. They are used. After their lifetime, they have to be discarded. So they are there in the system. They are also detrimental. Okay. So toxic chemicals are an important aspect, and very few people even consider this in their research and development. Okay. What about wasted solar panels? So 2050 is the year of, we are in estimation, we had already the population 10 billion, the energy requirements 900 million terajoules. Here, if we consider such solar panels worldwide, not talking about India, it will be around 18 million metric tons. What will you do with them? Okay, so all of these constitute environmental hazards. Okay, therefore we cannot strictly call this technology as green energy technology. So we, even though in practice we call it as a green energy technology, in strict sense it should not be called. It is clean. Okay, now lithium-ion battery technology. This is another very famous technology. Many people work on it, but most of them work on only one aspect, to increase the specific capacity of the battery, storage capacity of the battery. And very few people work on other aspects which are more important than increasing the storage capacity of the lithium-ion battery. So if I take lithium-ion battery technology, if I want to have 1 kilogram of battery materials, I need to mine 500 kilograms of various materials. So if I want to have 1 kilogram of lithium, I need to use 20,000 lakhs of water to mine. And where does this 1 kilogram go? It goes in at the maximum 10 cars. 10 cars. And you know, each battery stack, if I'm considering a 10 kilowatt hour lithium ion battery pack, it's about 200 to 300 kilograms on the car. Okay. In that you have electrode materials, cathode and anode. Cathode maybe about 10 kilograms of cobalt, nickel containing materials, lithium containing materials. Anode, graphite, if you consider the commercial ones, it's about 80 kilograms. Okay, so in order to get these materials purified and put them in, there is a lot of processing. That processing causes a lot of environmental problems. How much? If I'm talking about manufacturing a 100 kilowatt hour lithium ion battery pack, that manufacturing of one battery causes 16,000 kilograms of carbon dioxide emission. So you can decide whether this is a green technology or not. Now, in terms of fossil fuel equivalent, you have to expend 300 liters of fossil fuel in order to produce one working battery, not a battery stack, one battery. And how much that battery can store? That can store energy that can be produced by burning only 1 liter of fossil fuel. So if you burn 1 liter of fossil fuel, you know how much of energy can be obtained. Only that much of energy can be stored in one lithium ion battery, which takes about 300 liters of fossil fuel to be manufactured. So you spend more fossil fuel, 300 liters, to make a battery that can store only energy corresponding to only 1 liter of fossil fuel. So it's not even efficient. But still we use these batteries. We want to replace all the automobiles and make all the automobiles EV. And we want to charge these batteries using the conventional energy sources. Now, where is the energy coming from? It's again from the conventional sources, right? So right now, as I speak, these on strict basis, these are not yet green energy technologies. Okay. What are the other lacunae in lithium-ion batteries? The ones which I've highlighted in the red, you see, you want lithium and other materials. These are commercial cathode materials. Electrolyte also has lithium, and then the housing has nickel. Cobalt is also there in the cathode. Where do you get these materials from? You have to export pollution to somewhere else to get a lithium-ion battery working in India or US or Germany. And those places are only 5 or 6 in the world. For example, in the case of lithium, you have to pollute Bolivia to mine lithium. You have to pollute Congo to mine cobalt. Then we'll have those materials transported to developing and developed, so-called developed countries. They make these batteries and use. And these countries also don't make the batteries because it causes a local environmental effect. So they'll have a production plant somewhere else. Okay, so you see, you are only exporting pollution somewhere else and claiming that we have so many EVs, we are protecting our environment, but forgetting that these places are also on this planet, and at some point of time, the pollution will actually migrate and to other places too. Yeah. So, what are the problems? We import lithium. As I said, lithium mining has so many environmental effects. Drilling, water, and lithium sources are there where clean water is there. When clean water is there, people are there. Agriculture is there. So you're disturbing the entire environment there. Okay. Ethical issues are there. There is no protocol whatsoever in mining, irresponsible mining, and social impact. You have to displace people who are native to that place in order to mine there. You say, please go somewhere else. We have lithium here. And same is with cobalt and nickel, and we often forget about associated materials. Electric cars will not have engines, they have rotor and stator. Okay, these are permanent magnets, and again we have a problem with materials. These are not available everywhere. Each electric car like that, which I displayed in one of the previous slides, needs about 5 kilograms of permanent magnets. Who will provide? That's a big, who will mine? What is the pollution related to that? So that also has to be considered, and very few people work on associated materials. Okay. Poor recycling technology in countries like Sweden and Germany, in order to introduce any technology, like for example, energy technology into the public, you have to prove and introduce a recycling technology first. Then only the government or the policies allow you to introduce the energy technology. You should have a recycling technology first and then the original technology. Okay, so poor recycling technologies and of course poor policies. Mining related, human and child exploitation, equality in Congo, because these the ores are available in narrow paths. Children are used to mine. Humans, children, small children, because they can enter the narrow paths and get the ore. Okay, and you see how other so-called developing countries and developed countries are exploiting these countries in getting cobalt. Yeah. Equality, how much they are paid? Not even $1 per day, if you're talking about, and they get less amount, but their health, you see how much health is deteriorated for them. And battery imports, for example, India imports manufactured batteries by spending about dollars, this is US dollar, 1,000 million per year. We give some to Korea, come to Singapore, come to some, and then get batteries dumped into, working batteries dumped into India. This is not because we want. This is not because we cannot make. It's because the trade understanding between two countries. So if we don't buy this, those countries will not buy some other product from us, like let's say rice from us, something like that. Okay, it's not that we want so much of batteries, or by spending so much. Those batteries will be very cheap in those countries, but they sell it at a very high price to us, unfortunately. So through EVs, we don't eliminate emissions. It's straightforward. Electric vehicles, you don't eliminate emissions. You will only transport to some other countries which are weak, socio-economic weakness is there in that country. We export them, and then we have EVs here. Now, another buzzing technology is green hydrogen technology. How many of you know that There is a gray hydrogen, blue hydrogen, and then comes the green hydrogen. Hydrogen has been produced as for a long time using fossil fuels. 90% of the total hydrogen produced right now is from the burning the fossil fuels. Okay, and there is something called blue hydrogen, which is produced by using renewable energy. So therefore, the term blue hydrogen is given to that. But that is not an efficient process. But still, people want to promote gray and blue because they don't want any disruptive technology, because that will spoil their business plans and all. Only handful of companies are there throughout the world. They still want to promote fossil fuels, burning of fossil fuels, like Shell, for example. They can, if they want, they can also promote green energy technologies, but that would be disruptive for their business, for example. So they don't want. So the policies are also like that, unfortunately. So policies are promoting blue hydrogen. They are saying that this is produced by using renewable energy, even though scientifically it is well proven that it is not an efficient technology. Okay, we need humongous amount of green hydrogen. That means production of hydrogen without causing any environmental hazard, or with minimal environmental this one. So for that you need bulk hydrolysis, because it is through splitting of hydrogen, splitting of water, you get hydrogen. So there is no, right now when as I'm speaking, there are no efficient electrolyzer systems which can actually convert water or split water and produce hydrogen. Okay, and of course demand and supply relation is very poor. If you read the literature about hydrogen requirement for EVs and all, it's not much. The demand is not there. Okay, and system level electrolyzer, for example, if we have seawater, it can be also considered as a renewable source. There are no electrolyzers or system level where I can say I will use 100 liters of seawater and get hydrogen out of it. Okay, so such things are not there. That is a big lacuna in green hydrogen technology. And of course, once you produce hydrogen, let's assume that we have a green hydrogen technology and we have hydrogen called green hydrogen. There are no systems to store it or transport it. Okay, efficient systems to. So we had a call recently in DST where the DST has asked for proposals in which old pipelines which are already there for transporting, can they be converted to transport hydrogen, something like that. That's a high risk project, but people are thinking in those lines. Now, other lacunae, poor understanding on the overall scenario. We don't connect different points. We are only worried about a small problem which is given to us. We are happy to solve it without connection to other things. Okay. Poor academic and research training. And most often the research reporting is hyped or overstated. Okay. As you can see, we are mostly worried about getting a paper or a patent, but on one hand, we also know that this is not complete. Okay, we got a paper, but this is not it all. Yeah. And we hype that. Otherwise, if you don't overstate or hype, you cannot publish or get a patent. We had a meeting which was organized by TIFAC on this campus, and there was a question that many patents are failing when industries are trying to use them. What is the reason? The reason, then I asked the question, who are the ones who are reviewing the patents applications? They should be qualified enough to vet the patent, screen the patent, and they're mostly bachelor's or master's students who completed masters and got the job in such offices. They are screening those patents, so they're not competent enough to even screen the patents. So I was then told, don't split the thin hair further. Don't discuss such things. It's very important. If you don't solve that problem, in countries like Germany, if a reviewer is reviewing the patent, he is competent enough to decide whether the material or the claims contained in the patent are really worth patenting. Okay. But here we are in a different mode altogether. If we have a list of patents in my CV, I'll say, yes, you see my CV, I have 17 patents. Do you have? No. Okay. We only limit our thought process only to that extent. But I also wanted to give a talk on what is actually the patentable material, which probably in the due course I'll give. Not all research outcomes are patentable. Just because there is a process of patenting, we should not patent. Okay, that's my philosophy. Anyhow, you may not, you may want to take or not, but anyhow, not many work on allied green energy technologies. This is a big lacunae. If we say lithium-ion batteries, I will only work on anode material. I will only work on cathode material, but very few people work on system level and connecting the lithium-ion battery to the grid, or combining the lithium-ion battery storage with the renewable, like a solar cell. Those things. What are the recommendations then? Okay, we'll start with the academic, which maybe if you want to take them and incorporate in your work R&D, they might be useful. Okay. Now, first thing is you should do design-based research. Then you can reduce the resources, the amount of time you spend on the research. But do we do design-based research? Do we design our experiments before doing our experiments? Very few people do that. Reporting the reality. You see, any thesis you take, you will seldom have negative results in the thesis. All are positive results. You will not have any failures in the thesis. Right? As if the moment you did an experiment, it was a success. It can be if it is a design based, most probably. Yeah. But otherwise, there will be failures. You might have failed in some experiments, then you might have corrected and then got the positive, whatever you wanted. We should also report the negative so that others don't waste their time. Yeah. And so when we do materials engineering research, a lot of processing is there, a lot of manufacturing aspects are there. We should incorporate mass and energy balance calculations. First approximation, we don't need to go to cost analysis, whether my process is simple energy balance and mass balance equations. Okay. We calculate how much of energy is put in my process. Is it efficient enough? Even if it is not efficient, you report it is not efficient. No problem. But you make it a culture to incorporate mass and energy balance. If you are saying I'm converting biomass into energy or energy storage material, in the process, how much of energy is used? Is it worth doing that? What is the conversion efficiency? We deal with biochars. You take 1 kilogram, you will be left with few milligrams. Is it worth doing such research? For publication, yes, you get a publication, but you should not hype that. Okay, you should report if the conversion efficiency is 20%, it is 20%. Okay, and then you should encourage scorecard based reporting. And when we talk about sustainability aspects, there are several descriptors I said in the beginning. You should have those descriptors in place, and you should, if you talk about my process is sustainable, cost effective, we use these words, green, cost effective, sustainable. But do we present any data related to that? No. When we say cost effective, that means you should have done cost analysis. If we say sustainable, you should consider the resources, the process, the byproducts. What are you doing with the byproducts? Is it a continuous? Will it be available throughout? That analysis has to be done. Efficient, which efficiency? Energy, mass, what is it? If it is energy efficient, you do energy balance calculations. How much of energy you are inputting, how much of energy is used, wasted, how much of heat is generated, how much of units of electricity is used, what is the man? No, no. Okay. So such things, we should consider in our research. It's not difficult. We have recently started. We have not done till recently. In one of the recent papers, the reviewers and the editor asked us to incorporate. If you want to state that your process, you might be knowing that it is energy efficient, sustainable, and all, but prove it in numbers. So we did some first approximation calculations and incorporated, and it was accepted in ACS Sustainable Chemistry and Engineering. Okay, you'll see a paragraph of these first approximation calculations. Okay, and then we should consciously link to SDGs, which I mentioned. If we do that, then a sort of responsibility is there in conducting research. We attach. I'm saying that I'm trying to achieve SDG 7 or 6 or whatever in your research. Consciously attach. You may not achieve whatever is prescribed by the United Nations, but at least you're making an attempt through whatever research you are doing to connect to an SDG. That gives a little bit of responsibility, okay, towards the environment. So most of us deal with materials processing, whether it is pure metallurgy or functional materials or anything of that sort. When we do something, we should consider always flow reactor type synthesis. Whether the protocol what we are developing can it be extended to a flow reactor type? Flow reactor type is always prescribed in chemical engineering for sustainability and energy savings and carbon dioxide savings. Okay, there the resource is identified, a continuous resource is identified, process is continuous, the byproducts are taken care of. For example, if I'm doing pyrolysis, the resource is a biomass, pyrolysis is a process. In the process, when you burn the mass under controlled environment, byproduct gases, sign gases are produced. Okay. In my research, I should collect that sign gas and use it for some other purpose. That's a flow reactor type of setup. I will not talk about sign gases. Very carefully write in such a way that manuscript goes through. Yes, it can go through, but as a responsible lab, if it is so, yes. If I'm collecting, then how am I collecting? How am I using? That gives the sustainability aspect into the that brings sustainability aspect into the okay. One should also consider high throughput processing. You should have design based processing technologies. So what we do mostly, we adopt or we replicate whatever somebody has done, but we spend very less time in designing reactors of our own, which we know that something is working. It may work more efficiently if we have a reactor of this sort. We may know, but we don't go a step ahead and design that reactor, or not even try to design such a reactor. And now, when there is a problem of byproducts and hazardous byproducts, hazardous gases, you should do alternative chemical assessment. That is to, and fortunately, you have now AI, ML, and IoT, so you can do screening before even trying to do an experiment or developing something to see which system or which material system will give the least greenhouse gas emissions or least amount of hazardous byproducts and all that. And of course, you can accelerated novel materials development and materials replacement. If you can actually do use these tools, figure out, screen all these before even starting the experiments. When it comes to startups, there is again startups. Starting up is a very big buzzword. Many want to do. I have a startup. I want to do a startup and all that. But you should rank them. Get their ranking for the technologies by sustainability parameters. Nobody does that. I have a startup. Let's say it is a big thing. You are a great guy to have a startup, but is it really good for the environment, especially when it is related to the green energy technologies? I had a confrontation with one design engineer from Ola. Yeah. His concept of sustainability is uh, selling their products to get a break even. When I am talking about economic, okay, but I'm talking about another aspect. Yes, in his view, his company gains, profits for his company, economic growth for his company, for his technology. Okay, but what about the break even for the environment? They are starting, by the way, a gigawatt battery manufacturing hub in Bangalore or near somewhere in Bangalore. But I don't know whether they are considering the sustainability aspects. Where do they get the lithium from? What do they do with the manufacturing of those aspects? He has not ventured into. So, RRR technology should be made an integral part of lab research. RRR is reuse, reduce, not that RRR. He's smiling. Recycle, reduce, reuse, recycle technologies. Now these are actually becoming very popular in India. RRR technologies, especially with respect to plastic. Okay. Keep improving the efficiencies. I'm not saying that you should stop research on improving the efficiencies of the energy conversion, like say solar cells. Keep increasing, no problem. You keep increasing the storage capacities of lithium-ion batteries or secondary batteries or super caps, no problem. You keep improving the efficiency of transporting green hydrogen or hydrogen, no problem. But that has to be done while also doing the other things. Okay. Yet, yes, at some point of time, these increasing these efficiencies and some research on the other aspects may turn into a snowball effect, and then you can get this break even where you have a very good mass balance and energy balance, and while you are meeting the energy requirements for the future and the present, you're also protecting the environment in a nice manner. Okay. Manufacturers, NMDC, I don't know how many of you have seen their logo. They use the word responsible mining. Huh? Yes, it's very nice, but I don't know if in practice it is responsible. But especially with respect to these specific materials like lithium, because now they're so precious, they're made precious. Okay, like cobalt, nickel, manganese. Uh, Responsible mining is very important. Should strictly, they also should get the ranking by sustainability parameters. There are institutions now which, if you the manufacturer goes to them, a third party, but they don't go because then they'll their story will be out. So yeah, integration of green energy technologies with existing grids. This is actually many. We can actually, as engineers, can work on that, but very few people work on utilizing the existing grids and connecting. Like we have here, right? It is somebody like the life sciences which I showed. It's actually grid connected. Grid connected means there is a when the sunlight is falling on the cells, and then there is an inverter, there is a supply of energy, there is storage of energy. That is a continuous process. But what I'm saying is such things should be done on a larger scale. Yeah? And of course, we should see that whenever there is a disruptive idea or a happy accident in the lab, that you discover something accidentally, one should encourage. Okay, but most of the times we want to go conventionally. We say no, let my student do this work. Why I don't want to venture into that new area. Okay, for example, blue versus green. We should strictly stop encouraging blue. Yeah, we should say if you produce green, then don't talk about blue hydrogen. Okay, but the policies are in such a way that you have to support the blue hydrogen because it is produced by using the renewable sources, even though if it is not efficient in the process or efficient with respect to the greenhouse gas emissions. Strict and realistic regulations and policies. You should say recycling first. And culture and public, it should become a culture, and public, we all should participate in such things, in even in simple things. Like when we go out, we say switch off. That we are still have to remind somebody. It is not in culture. Some the last person, if he or she is not trained, they'll just leave it and go. Okay. So that has to be an aspect of you should get trained. Otherwise, such things won't work. Of course, human exploitation is there, and subsidies and tax incentives. For example, there's a company which wants to, which says, I have a technology, green energy technology. The government is giving a lot of incentives and tax reductions for that company without assessing whether really that technology is green energy technology or not. Okay. It should not happen that that it is, maybe it is convenient to leave a waste in the as a landfill than bringing that landfill into the public and creating more or generating more pollution. Okay. Let it be in the landfill as of now, because there is no good technology to convert that into a better material efficiently without affecting the environment. Okay. But there are companies which project themselves, hype their technology and show a patent. Say, you see, I have a patent, so why don't you? But there is no policy where patents are checked whether it is worth patenting or not. Recently, I was in a defense, and then the student was mentioning on the slide. The student has written that this work has been published or submitted as a patent application, and it is now published. He's very proud to announce that that work is submitted as a patent. As I said, okay, keep that patent aside. Your XRD pattern is not properly indexed. So that patent contained this XRD pattern, which is wrong, but it has passed several stages, and maybe in the future, in the coming days, it may be also granted that work may be granted a patent. That means even wrong information incorporated, scientifically wrong, it's fundamentally wrong, basically. And the answer that comes from the supervisor and the student is, I will correct it. We will correct it. How will you correct it? When it has passed, you will tell that what I gave is wrong. You cannot do that. Okay. So such things we should avoid. They're very simple to avoid. You have to question yourself, is it correct to do this? Okay. Anyhow. Yes, because this lot of money is spent on this, but with very less outcome, or which is useful for the society. Thank you. Any questions? I'll be happy to answer.
Okay. Sir, see, basically, the definition of green energy itself has the lacuna in itself. Therefore, can't we make it more robust one? Therefore, the definition itself has a shallowness in itself. You mean to say, I mean, like environmentally, it should be friendly like that. Therefore, the green energy definition, what we have, I believe should be revamped so that it includes. It means, I said that the cause and effect bound to be there, sir. cause and effect bound to be there, and we cannot compromise on what we call the energy requirements of the society or the world at large. And if you go like this and
impact or minimal impact on the environment. So we always looking for the baby. Working for the baby where energy requirement impact at the same time the carbon footprint is but where are the technologies? That's
that also have to be changed, sir, so as to so as to conform to the standards.
any other? Yeah, RRR.
As you mentioned about that clean and green, in that about synthesis, whatever photosynthesis part, that is going to be in green, like very green, ideal green. So how that fertile land becomes non-fertile? So in that, like earlier, it is photosynthesis and lot of plants, it's growing well. After like few years, and it's going to be soil is going to be non-fertile. Yeah.
Okay, your question is about why?
Yeah, so soil, like anyhow degrading in the soil quality.
Wherever human intervention was there,
Okay.
wherever unplanned, wherever intervention without its design,
So with plant also, so,
plant with soil, who did this? Soil asked, whenever this
yeah.
development, we have gone too far, and now we are want to revisit the cycle.
Okay, sir. Yeah, thank you.
So, I have this classical example of water purification. Many of the water bodies, natural water bodies in the eastern part, like Kaukala and wherever these mines are there, they also have drinking water ponds. West Bengal. So what we humans thought that the iron steel very good material. So we need mine. So we have mined all those holes, which were actually protecting the water ponds from natural pollution. For example, acagnite, iron oxyhydroxide, by virtue of its crystal structure, it actually absorbs critical like lead, chrome, they were naturally there around the ponds, protecting the water from external lead and all to diffuse and reach the water, and that is agitated, they will reduce their energy by polluting the water. But actinides were there around, but we wanted iron, so we mined such minerals and created an imbalance, allowed the natural contamination. Now we are saying actinides are good for water purification. Now we are saying actinides, use actinides, you can purify contaminated water, lead. You only removed them from the nature. Now you are saying you put the actinides around. So that was that some people, engineers or scientists, wanted many. That is why we are talking about all this. We go by design based, give a thorough thought on the experiment be done or not. In our lab, we used to use hydrogen for reduction when we started. At some point, they said, don't do such a don't need hydrogen hydrate with the excellent reducing agent. We used to use to chemically reduce the vacuum. But you should be very well equipped, very well trained to handle that chemical. You should have excellent facility to store it. You should have excellent fume hood to use it. I cannot do it in normal. At some point, I don't use it like this. It is not good. But the researcher and the outcome is not important. Like sacrificing something for the help of me. We talk. We said, use some other ways of which are better ways than so such things time change that is that not that I am doing it. I want to learn it.
The record of survey Finland is supposed happiest step. Is it that because it is foreign sustainability development?
Not only that, that is one aspect. They also have several other education, primary education. Start with that. Well, better. It's big effort to accept it. It accepts. Might have experience, but why do I take in a train like that? The problem behind we come from different places, different different places. So all are not trained in the same manner. But give an idea, among 100, one I like it. After 99 may not like it. Then it can be the other way also. So it depends also on they are the small country and over the years they will whatever you policy. If Sweden says I will not use lithium ion battery technology because I am worried I don't want to create I don't want lithium ion battery technology. I will not exploit these fully. That stand the government has to take. UN cannot. Their quota, not their quota, right? What is it? The only place from where our markets are launched, or maybe recently they added one more place. But that's the main way. The scientists have found that geographically and otherwise they can do, but that land, that island, belongs to somebody else. What you have done for the sake of the space technology, it is good. Yeah. So you have displaced the natural, the original tribes of the place. Let go there, go somewhere else. You want to have a launch pad there. That's who takes.
Why don't we address that level before it's a top 10?
No. Government seems to address, but at the end of they end up not addressing. They have to policy are there. So now their own land, they have to take permission to go inside. Yeah. Williams was a weak country, so small population. They are affected from the we do not have that. That's a policy. Strong enough to take India, for example, can also tell. I am not. I don't want lithium ion battery. I work on aluminum technology. So if at all you want to exploit, you'll exploit your own resources. But
I actually joined little late. I don't know how much you discussed about the energy that is powering the electrical vehicles. That's where I started actually. You said some fossil fuels are used, right? Inside, that is, I accept coal when it is used, absolutely yes. And right now we are getting power largely from Srisai, which is hydro. And Kalpakam, we have this atomic energy. So if atomic energy can be used to power the electrical vehicles, so in that case, what is the balance? Is it sustainable in that way?
Very much sustainable.
Ah.
But it will be fusion energy.
Fusion energy, I accept. In fusion energy, we talk about no emissions at all. Here we have nuclear emissions, but not CO2 emissions.
Correct.
Right? In
But
that,
no, not nuclear emission. Safety is an issue for fission.
true.
The emissions, as I said, but waste is more.
Which waste? Nuclear waste. Yeah, that's what. Nuclear waste is there.
More in fission.
Fission, but is it contributing to climate change?
Okay. In order to answer effect of climate change, of storing or disposing, we have not yet generated system.
True.
Right? Second thing, cannot install as of now, as per the agreement among the world nations, world countries, cannot arbitrarily install these plants everywhere.
Yeah, it's highly restricted
So the
in that way.
transportation of this grids and all is a major. Otherwise, on paper, if you do, it's a vision or fusion can be very efficient.
Yeah, I mean, is that the reason why world is going behind this electrical technology altogether?
But at the same time, we should also be working on these technologies.
Which one? Nuclear
or
yeah, fusion technologies also people are exploring. True. Since then, I don't know when it will become reality. Fission technology is there at least.
It is there.
Compared to coal-based power generation or fossil fuel-based power generation, if we are sticking ourselves to at least atomic energy, is it better? That is the.
It is on paper better, but again the policy and the agreement, because if we say we want to use fission for powering our EVs, nobody is going to believe. And we cannot on our own, let's say India, cannot take a decision, even though we are a sovereign, independent country. We cannot say we will use the fission for this. Okay, they are bound by other facts.
Power comes from different sources for the country. One of that is definitely fossil fuel.
And yes, it is that this can be a very efficient way of powering, because we can increase the number of, but the amount of power that is required to charge them, if you don't develop those, again there is a problem.
Yes. So, and overall about the hydrogen energy, you are positive.
Yeah.
Green hydrogen, you're positive. But as far as storage and other things are concerned, right now EV is getting commercialized, but not hydrogen-based vehicles. Okay, so that is far away.
Hydrogen-based again, for small vehicles like cars, it is found to be inefficient.
Oh.
Fuel cell-based hydrogen-powered fuel cells for small cars are efficient.
So is it the problem of technology? If it can be made efficient.
No, it is not the problem of the technology. The same technology is efficient and for heavy trucks.
Yeah, I mean, is it the hydrogen technology right now we are talking about, or the physical laws themselves forbid that it cannot be efficient for small vehicles?
Physical laws for small systems, for moving, for stationary applications, it is very efficient.
Okay.
For small vehicles, like suppose we have our cars.
Yeah.
If I want to have a
hydrogen fueled car,
that is not efficient. But if I consider heavy trucks, 40 kilometers per hour, 60 kilometers per hour, then fuel cells powered by hydrogen is efficient.
Okay. So this efficiency is what? Efficiency of what?
Efficiency of so you spend more in the case of more energy is spent when you power cars like small.
Energy spent, meaning hydrogen based energy only. I mean, we are not bothered, right? Let us spend more energy also because impact is not there.
That is also true.
Ah.
You want also the speed.
Yeah, those things. If
Safety comes into the picture. For
okay.
example,
Oh.
I want to go 120 kilometers per hour
Hmm.
using a car which has a fuel cell filled with hydrogen,
Okay.
liquid or gas. It is dangerous.
So this is a technological.
That is
This is a technology. Safety wise, if we can contain that, it is possible. So
or
I mean,
if you have a solid state fuel cell, then yes.
So I think this seems to be very good. I mean, if at all you are suggesting one of the field in the recommendation, to the research can be focused on this in order to get more less environmentally impactful technologies, then hydrogen is the guy. So research wise, if at all we focus more on that, it's a good way forward.
And if you see hydrogen, recently there was a call, SEST call on exclusively electrolyzers, not fuel cells. Fuel cells give the energy, but for that hydrogen needs as a fuel, which hydrogen is produced by the electrolyzer. So if you don't have an efficient electrolyzer, there is no point in the fuel cell working efficient, right? So they have given a special call. They've identified 7 or 8 topics related to only electrolyzers, and one of them is electrolyzers whose input is saline water, seawater electrolyzer. Desalination, it's a system level, not the lab level. The system level, so many liters, so many kilowatt hours, so they are all identified. They are known for quite some time, but I see that BST is also now in the way of emphasizing that.
Okay. I mean, there at least the focus is on developing hydrogen. That is
I've
good.
shown one slide. I'll show you. It is very interesting.
I didn't see this.
Sustainable Development Report. How much of renewable energy share is in the total final energy consumption by different countries? A lot of percentage-wise, more than 80%.
Okay.
They are incorporating renewable sources in their total energy consumption. In fact, we are better than China and United States.
Okay.
That is because the last 10 years, India has made a tremendous progress in solar.
Solar, yes.
Likewise, if we also bring in hydrogen, then
so
this graph
possibly this is why DST also is in this direction. Oh yeah,
both far better.
This goes only to 5,000, but then maybe per person.
No, actually, they have achieved these SDGs of 83%, 85%. Possibly because energy-wise they are also better.
They are other way also. They have
the other things also they are better.
Gasoline.
Yeah, very good. And especially the last one about the publications, where let's say, for example, my work, I do some alloy design, then cast the alloys, heat treat the alloys. There is some energy involved in all that. Do material balance, energy balance for all these things. Put a table in the publication or in the thesis.
Exactly.
Something like this. If
that's what
no, but even if the process is leaving some gaps, that's fine. Just record it. Record it.
It becomes an habit.
Definitely. Actually, that reminds me about one example. The Calford Journal. Previously, people were publishing in that. The main thing there is the Gibbs energy description. People have to give a file which can be used by anybody just with click of buttons, but nobody gives that file till 2010 or so. But after that, it is mandatory, so they have to give. So if publishers, I think it's a big scientific movement I'm talking about.
The same is with many of the ACS journals. If you want to report any sustainable energy technology, they have a list to be filled.
Oh, very good.
If you meet only that, you can submit.
Okay, I mean, at least you give all the data, or there is some category value
for example, number of cycles. Let's say I'm reporting about lithium-ion battery.
Okay.
Number of cycles should be reporting about 1,000 or 5,000 is fixed.
Okay.
If you have done your experiments less than that number, you cannot submit it to the journal.
Okay.
So such
Things are
descriptors
there.
are
Yeah, I mean, if it comes for even researchers like ours, we never bothered about this material balance, mass balance things. What arc melter I'm using, how much energy goes in.
exactly.
Heat treatment, if I do, how much power I'm
Power.
using. So these things, if I calculate and then give that as a number, if not in a publication, at least in
At
the
least in the
university
thesis.
level thesis,
Yeah,
that is a
In
good
fact,
thing to
I
do.
suggested to this IQAC, and probably in our school board we should
Actually,
have
I
this
was about to say, we should consider that in, put it in our
as a
thesis.
statement.
Ah.
In your thesis itself,
Yeah,
one page.
this you suggested. That is basically how your research is related to sustainability.
But
Fine.
what you are saying is another aspect.
One more level.
Technical
Technically, numbers.
numbers.
That is a good thing to add.
First approximation is better.
Yes, yes, yes. Something.
Yeah.
So you talked about solar as well as wind power, but what means not hydrogen, but hydro what from what?
Very low right now. So see what happens. You have to count Newton's second law. The losses, no. So to count for the losses, it is very difficult in certain technology. Yes, they are available. The thought is there. Wind to electricity. But what about the bearing? When you want to move the all the technologies, but it is more in certain renewable related to renewable technology. Okay? That is why when we calculate the efficiency of conversion, the numbers are less. In the case of solar, in the case of fusion, the numbers are very high. Therefore, obviously, it attractive, right? And the progress in research in those areas is very less. Okay. So first of all, the numbers are less. The conversion efficiency numbers are less. See, most of us think that solar photovoltaics is very popular. But among the solar technologies, solar thermal gives the highest efficiency, not solar photovoltaic. If you see the solar energy, the solar is to convert the light into heat and then to whatever electric energy. That's actually a convert, right? That is more efficient. The percentage of conversion is more efficient there than solar photovoltaic. But we, as common people, when we say solar technology, solar cell means it is photovoltaic. But the voltage generated is so less. For domestic uses, it is all right. But if I want to power an industry, I will not have panels. How many panels? How much of land is needed? Okay. Instead, I will use solar thermal. In such cases, okay. So such details normally we don't look into. But when we do research, we should also know all those. That is what one of the recommendations is that to know the overall picture and where you are, so that you don't talk hype science or technology. Otherwise, you'll end up saying, I have done so much, I have 5 publications, I have so many things, I have patents, I have 20 patents. You can speak like this, but in reality, where are you? That is important. If it doesn't become a culture, we will be like this. 20 years later, somebody will be such a presentation. Then an incremental advance. Right? We'll stop here. Thank you for attending. And we'll meet next Friday. Who will next Friday? Next Friday, you have to coordinate.
Yeah, but you have to pick.
Yeah.
You have to take the lottery. But pick it now. One day, they are ready for the